Today we're going to look at electricity in the home from the paper 1 GCSE Physics paper. We'll start off with alternating current, or AC for short. At home the frequency is 50 Hz. That means it's alternating or changing direction 50 times every single second. And we would draw alternating current like a transverse wave as shown here. I've then turned this into a graph where I've got voltage or potential difference on the y-axis and time along the x-axis. Although the potential difference comes in at 325 volts, it averages out, as you'll see later, to about 230 volts that we use on electricity supplies in the home. An equation links frequency to time period. Time period is the time that it takes for one complete oscillation, so from there to about there, so how long it takes, and that equals 1 divided by frequency. We receive our alternating current, our mains electricity, from the national grid. Straight after the power station, there's a step-up transformer, and that sends the electricity to the national grid. And what it does is it turns the 25,000 volts from the power station up to 132,000 volts that get sent via the national grid across the country. By the time consumers use the electricity, there's a step-down transformer that converts it back down to a more usable potential difference of 230 volts. The reason we use a step-up transformer is to decrease the current, and what that does is it means less energy gets lost as heat. It makes transporting the electricity across the national grid far more efficient. So of course, by the time it reaches our house, we need to know all about plugs. So here's my drawing of a 3-pin plug, and you need to know all about the different wires, but also this thing here called the fuse. Let's start with the middle wire, the green and yellow one, also known as the earth wire. So that then will get connected to an outer casing if it's made out of metal. So if that becomes live, it can take the excess electricity back down to the ground. So most of the time it stays at 0 volts. The brown wire, or the live one, carries the current into the circuit, and that's the one that has 230 volts. It's the dangerous one. As you can see, that's the one that's connected to the fuse, and that's a safety mechanism. So should the current get too big, the fuse will melt or the fuse will blow if the current gets too high. The live wire then brings the current into the appliance, and we need to complete the circuit, and that's what the neutral one does. So the blue wire completes the circuit back to the national grid, so that's also just like the earth wire at about 0 volts. So here's the picture all together, and it's just a case of knowing which colour wire goes with which name. Let's start looking at some of the equations that go with this topic, and the first one's power. So you've seen this equation before, how quickly you transfer energy, or power equals energy transferred divided by time, but now we need to think of it in the electrical power format. So power equals current times potential difference, P equals IV. Power, of course, is measured in watts, current in amperes or amps, and potential difference in volts. And there's also another equation for power. Power equals current squared times resistance, or P equals I squared R. Again, watts, amps, and resistance, of course, is ohms. The main thing that this equation tells us is if we double the current, we increase the power by a factor of 4, and that's because if we do 2 squared, because of the squared term, 2 squared equals 4. Let's continue to look at more equations, and the next ones are based around charge. So charge equals current times time, or Q equals IT. Charge is measured in coulombs, current in amps, and time is always seconds. As a reminder, a charge is anything with a charge. So for example, an electron has a charge of -1, so that would fit just here. However, when electrons move, that's when we refer to it as a current, and it's how quickly they move that tells us what the current is. So quite often the equation is written current equals charge divided by time, the rate of flow of charge. So when a charge flows, or electrons are moving, through a resistor, energy is transferred to the resistor, and this often will make the resistor become hotter. So then there's an equation that links energy and charge as well. So energy equals charge times potential difference, or often written E equals QV. Energy in joules, charge in coulombs, and potential difference in volts. Next, energy equals power times time. The eagle-eyed amongst you will notice that all that is this equation from earlier that's been rearranged into energy equals. However, power equals current times potential difference. That's what we wrote over here. So now I can write energy and energy. Rather than writing power, I can write current times potential difference, and then I can keep the time just here. So we now have another equation, energy equals current times potential difference times time. At this point, it's also worth mentioning about efficiency, and that is the output power divided by the input power times 100%. So for example, if you have an efficiency of 60%, that means 60% of the power, or 60% of the energy, gets transferred into the useful form. And it also therefore means that the 40% gets wasted. Also linked here and commonly seen is 1 kW. That just means 1 kilowatt, or that's just the same as 1000 watts. So kilo refers to 1000. So 60 kilowatts would be 60,000 watts. That now brings us to the end of the video on electricity in the home. As ever, if you have any questions, please get back to me, and don't forget to hit the subscribe button so that you get alerted to any future videos. Thanks for watching.